We said only real numbers can be placed on the real number line. So where do we put all these other numbers if we can't put them on the number line? We have to come up with some other way of doing it, and that way is what we call the Argand diagram. Now, that way we can still represent all complex numbers, not just the real ones, geometrically. And it basically looks like something very familiar to us. It looks like the coordinate plane, because the x-axis, if you like, is our real number plane. We could call it the real axis. And what we basically do is we'll create an imaginary axis that's perpendicular to it, and it looks like the y-axis of our coordinate plane. We should now be able to plot any complex number, not just the real ones. A equals 2 is a real one, so of course we would place it on the number line. There it is. Something that's purely imaginary, I can place it on that imaginary number line, down there at -3. And something that's a mixture of the two, well, we'd just plot it like we would coordinates. Now, the real part is -2, the imaginary part is 1, so we'll go here at -2, 1. That's where that number sits. If I wanted to plot 4 minus I, the real part is 4, the imaginary part is -1, we're down there. So every complex number has a unique point on this plane. 4 plus I, okay, real number's 4, now the imaginary part is +1. And this brings up something interesting. If you're going to plot conjugates, those two numbers must be reflected in the real number line, because the real part's going to be the same, but the imaginary part's changing sign. So if we ever see 2 points that are reflected in the x or real axis, we know they're conjugates. How about this one? The negative of 4 minus I, so the negative of d, where will that sit? We plot that, and again we can see something interesting here too. The opposites, or the negatives of each other, the point will be reflected through the origin, which is a rotation of 180 degrees. Here I would be able to draw a line between D and F, and it would pass through the origin. This one's also what we take note of. If I was to multiply by I would get 1 plus 4i. And what we notice when we plot that one, there it is up there, but multiplication by I, we actually rotate it 90 degrees. So that's why when we multiply by -1 we get 180 degrees, because what you're really doing is multiplying by I squared. You've rotated twice. Every multiplication by I will be a rotation of 90 degrees. We now have a way of representing every complex number uniquely on a diagram. So locus, drawing pictures, that brings up some interesting things. If I want to draw a horizontal and a vertical line, now if I was talking coordinate geometry, I'd say, well, that's got the equation y equals c. If I'm talking about complex numbers, I can give it a different name. I can say, well, it's not y equals c, it's the imaginary part of z is equal to c. Think about it. Every point that I would plot on that line would have the same imaginary part. So that's a different way of writing the equation for that picture. A vertical one, very similar, they now have the same real part. That would be x equals a constant if we were talking about coordinate geometry, but when we're talking about complex numbers, that's the real part of z is equal to k. What about circles? Circles, centre at the origin, radius is r. Well, hang on, we know the equation of a circle is x squared plus y squared equals the radius squared, if we were talking about coordinate geometry. But we also saw x squared plus y squared was something important when we're talking about complex numbers. That was z times z conjugate. That would now be an equation in terms of complex numbers for this circle. Z times z conjugate is the radius squared. No, they asked me to describe this particular one then. Ooh, what is it? I don't spot it straight away. So if I don't spot it straight away, I'll convert it to coordinate geometry so I can see the equation, and then I might get what it is. I'll expand it out first, so z times z conjugate, and then I've got 4 plus I z conjugate, and so on and so on. And eventually when I play around with it, I'll substitute in the x and the y's. I could have done that straight away, left it to the end, it doesn't matter. But at some point I come up with something I can deal with because I know my coordinate geometry. I've ended up with this. It looks like it's a circle because I've got an x squared plus a y squared. Let's complete the squares on it so we can get it in a form we like seeing. Hang on, here we go. It's a circle. I know it centres at -4, -1. and the radius is 7. So it's a circle that's been shifted. And in fact, when I'm talking about complex numbers, this is what we see with a circle that's shifted. It's still the same idea. Remember when we shifted, we subtracted the centres. And that's why we got, x minus the x value of the centre, y minus the y value of the centre. Well, I can encapsulate that all in one thing by saying it's z minus the centre. The centre is the complex number omega. But it'll be multiplied by the conjugate of z minus the conjugate of the centre. That will also create a circle. This one here, again, I look at it straight away and no, it doesn't jump out at me as something familiar. So let's play around with it and try and get x and y's in there. I'll multiply both sides by z conjugates, and then I can, because look, on the left hand side I now have z plus z conjugate. Well, that's going to be 2 times the real part. So that's 2x. And on the right hand side I have z conjugate, and we know that's x squared plus y squared. Looks like we've got another circle here, because if I rewrite that one, I'll get x minus 1 squared plus y squared equals 1. So it's a circle, centre 1, 0, radius 1. But we have to be careful. Remember, you always go back to what the original question was. Does it satisfy that? I changed this into coordinate geometry so I could work out what it was. If you look at the picture, there's our circle. There actually is a point of exclusion, because if I go back to the original question, z can't equal 0. It's on the bottom of the fraction. Yet, my circle goes through the origin, which is the number 0. So I would have to exclude that point. So it is, in fact, all that circle except for that one point. It would not satisfy the original equation that we were dealing with. Okay. 1C.